Hello everybody. This is the first try of an online lecture that I'm going to prepare for you because we haven't done any math in more than a week and a half now, or 2 weeks. I'm going to go over section 13.1 again with you. Also, I have seen that you haven't done, many of you haven't even started the latest web work, which deals with this section. So I'm gonna go over some basic stuff with you one more time, and from the next video we'll start with the new material. Okay, so we talked about vector function and space curves, right? Or plane curves, depending whether we're talking in 2D and 3D. And those are given by vector functions, where each component of this vector is nothing but a function depending on a parameter t. So what this vector function does is that takes real numbers and as outputs, so the inputs are real numbers and the outputs are vector, such that the terminal point of these vectors basically describe each point on the curve, whether it's in 3-dimension or in 2-dimension. Okay. It is very important to note that every curve has infinite numbers of representation, and redefining the rule that describes the curve is called reparameterization. For example, the curve described by the vector function 4 times cosine of t and 3 times sine of t, where t is from 0 to 2 pi. Okay, if you remember, this was an ellipse. Okay, can also be written or reparameterized by the vector function, let's say 4 times cosine of t cubed, three times sine of t cubed. Okay, so basically, in a way, it's like a substitution, right? I have substituted the parameter t, I've substituted the parameter t with the parameter t cubed, and that is going to be equal as long as now the interval of t is going to change. So these two are going to describe the same curve as long as now t from the second parameterization runs from where? From cubed root of 0, which is 0, to the cubed root of 2 pi. So of course, as you can imagine, just by changing, adding or subtracting numbers or raising them to different powers of this t, right, you can have infinitely many representation of the same curve. For example, let's say second example, find the vector representation of a semicircle that goes from the point 2, 1, 0 to the point 2, negative 1, 0, centered at 2, 0, 0, in the plane x is equal to 2. Let t goes from 0 to pi. Okay, so it's a semicircle that goes from the point 2, 1, 0 all the way, so this is the direction, all the way to the point 2, negative 1, 0. Okay, first of all, let us address this part, the fact that the curve lies in the plane x is equal to 2. What does that mean? That means that the x component of the vector, so let's say r of t is equal to f of t, g of t, h of t. Okay, if for any t the first component, the x value is 2, That means that f of t is simply a constant. It's 2. No matter what t is, the output is always going to be 2 because the curve lies in this plane x is equal to 2. Okay. Now I want to remind you that whenever we're talking about the circle, right, we use the permutation, we go into polar coordinates, okay? So it's a circle lying in a plane parallel to the YZ plane. So if you have a circle in this plane, what is going to be the polar equation of this polar representation or polar equation of this curve, right? So y is equal to cosine theta, or in this particular case t, and z is equal to sine of t, okay? Because we're talking about a semicircle, t will just run from 0 to pi. We're not describing a whole circle, we're describing a semicircle, so t is going to go from 0 to pi. So there you go. The parameterization of this curve is 2 cosine of t sine of t. Also, I just want to remind you that a circle of radius r centered at the point AB is parameterized as follows. R of t is equal to r times cosine of t plus a, and r times sine of t plus b. Okay, so whenever we have to parameterize a circle of radius r centered at AB, if it's the origin, then AB is just going to be 0, then is parameterized in the following way. X is equal to r times cosine t plus a, and y is equal to r times sine t plus b. From here, x minus a is equal to r cosine t, y minus b is equal to r sine t. If we square both sides in both equations, we have x minus a squared is equal to r squared cosine squared t, y minus b squared is equal to r squared sine squared t. And if we add these two equations, you get x minus a squared plus y minus b squared is equal to r squared cosine squared t plus sine squared t. Cosine squared t plus sine squared t is the basic trigonometric identity, so indeed you get the equation in Cartesian coordinates of a circle centered at 8b with radius r. The next example that we're going to do is finding a vector function that represents the curve of intersection of the ellipsoid x squared plus y squared plus 4z squared is equal to 4 and the cylinder x squared plus z squared is equal to 1. Okay, so right away you have to identify what would be the go-to go-to equation. So x squared plus z squared is equal to 1. If you write x as cosine t, and if you write z as sine of t, then indeed x squared plus z squared is equal to cosine squared t plus sine squared t is equal to 1. In that case, the only thing that's missing is what? Finding how much is y expressed through the parameter t. Why? Because basically you're looking for a vector function r of t, that's f of t, g of t, h of t, right? So this would be cosine of t equals x is going to be f of t, z is equal to sine of t is going to be h of t. Okay, so the only thing that's left is expressing how much is y, and you go you find out that through the equation of the ellipsoid. So x squared plus y squared plus 4z squared is equal to 4. Y squared is equal to 4 minus x squared minus 4z, or y is equal to square root of 4 minus x squared minus 4z squared. We are underlining here that y is greater or equal to 0, so this is going to be positive square root of 4 minus x squared minus 4z squared. Okay, now in order to express y as a function of t, I have to express that through expressing x as and z parameterized through t. So this is the square root of 4 minus cosine squared t minus 4 times sine squared t. And here I can continue simplifying this in the following way. Square root of 4 minus cosine squared t minus 4 sine squared t is 1 minus cosine squared t. Drop the parentheses. 4 minus cosine squared t minus 4 plus 4 cosine squared t. Simplify the expression under the root, and you get square root of 3 times cosine squared t. So finally we can write down that r of t is equal to cosine t square root of 3 cosine squared t sine of t. And this is this vector function represents the curve of intersection of the ellipsoid given by this equation and the cylinder x squared plus z squared is equal to 1. I would suggest you to do the problems 42 to 46 from section 13.1 or 13.2. Let me check that.